Hello, my name is Robert Vaser and I am a postdoctoral researcher at University of Zagreb Faculty of Electrical Engineering and Computing. I'll be presenting you a deep learning approach to determining the type of long reads. Recent advancements of sequencing technologies greatly facilitated the problem of de novo genome assembly, but the problem still remains one of the most challenging ones in bioinformatics. The most common approach is the overlap layout consensus paradigm, in which an assembly graph is created by pairs overlapping all reads of the sequencing sample. Afterwards, a path is searched for such that it would attempt to reconstruct the original sequence of nucleotides. One of the main drawbacks of such approach is that due to sequencing errors and repetitive genomic regions, these graphs can be extremely complex. Therefore, it is necessary to simplify such graphs by identifying the problematic reads and either preprocess them accordingly or simply discard them. Based on overlap properties, we distinguish four types of reads: regular, repetitive, chimeric, and junk. Regular reads have a unique location in the genome and their coverage is uniform across all bases. Repetitive reads cover one or several repetitive genomic regions, which results in some of the nucleotide bases having a significantly higher coverage. Chimeric reads are products of sequencing errors where two or more distant genomic regions are glued together in a single read and have a characteristic sharp drop in coverage around the sites where these regions are connected. Finally, junk reads are those that have very low coverage compared to other reads, mostly due to higher error rates. One way to inspect read coverage is through pylograms or overlap stacks, both which are depicted in Figure 1. Pylograms are one-dimensional signals denoting pair-based coverage, while overlap stacks depict overlaps of other reads onto the observed one, that is, their beginning and end positions. On the top left of this figure you can see a pylogram of a repetitive read with a characteristic high coverage region, while on the right you can see its corresponding overlap stack. Same can be seen on the bottom of the figure for a chimeric read where a zero coverage drop can be noticed. Usually, read types are declared with heuristics, with manually chosen parameters based on analysis of several genomes. Here, we present a method based on convolutional neural networks with the potential of generalizing detection to make better predictions on unseen genomes. The first thing we did was create a hand-labeled training dataset of over 8,000 images. Reads were obtained from the Oxford Nanopore Zymo metagenomic dataset, covering 4 different bacterial genomes. Each read was inspected with the alignment plotter Gepard against the corresponding reference genome and classified accordingly. There was an approximately equal number of each read type, making the classes balanced. Two models that we tested were based on AlexNet and ResNet 18 convolutional architectures, which we applied to both pylograms and overlap stacks. Models were tested on a dataset consisting of about 2,000 images, which were also hand-labeled, while the corresponding reads were obtained from 2 bacterial genomes not included in the training set. Both models achieved accuracy of over 90% when trained on either pylograms or overlap stacks. However, the highest accuracy of 93.24% was achieved by ResNet 18 model trained on pylograms. In Table 1 you can see the corresponding confusion matrix we obtained. It can be noticed that most of the chimeric reads are correctly predicted, which will greatly aid in the graph untangling. On the other hand, a lot of repetitive reads predicted as regular, but that poses less problems since by this prediction no errors would be introduced to the assembly graph. We believe that the training and evaluation datasets are crucial for this problem, and that by creating larger, more diverse, and carefully labeled datasets, prediction accuracy could be even greater. This could lead to significantly simpler assembly graphs, eventually producing less fragmented assemblies in a fraction of the time needed in the layout phase.